Good afternoon and good morning, everyone. Thank you for attending today's direct learning session for OptiStruct, Structural Analysis and Optimization. I'd like to introduce myself. I am Darius Fadanelli, and I will be the moderator for today's session, and I'll be helping answer any questions that come along today. Today we have Eric Larson as a trainer. He's been with Altair for over 8 years now, and he's a specialist in our GUI and OptiStruct products. So I think you'll enjoy what he has to say and show today, and just in general everything else that we cover about the capabilities. So just a few quick notes before we get started. We do have everybody muted. That way when we are recording the session, it will allow it to be as clear as quality as possible. We will send out a link to this session to everybody that has signed up so that everybody can review this at a later time if they have any questions or want to see how something was done. If you do have any questions while Eric is reviewing the material, please feel free to go to the question tab, and I will be watching that and try to answer those, or make sure that when we do have the Q&A session at the end that your question gets answered. When we do end today's session, we will have two very short questions that will help us better understand how we can provide these to everybody at a better time in the process for them to use it for their next vehicle build. And also, if you would want us to get in touch with you if you want some more detailed training or information about this topic. One question that does come up in these sessions is there a student version available? And the answer is yes. There's a free student version available. To get that, all you'll need to do is to go to our website, and under the Academia tab, you'll see an option for a free student edition. You'll need to order it, even though it's free. Give some information about yourself, email address, your university, and it will then tell you how to get the necessary host ID so we can provide you a password and where to download the student version. So I won't take any more of time, and we'll get on to Eric so he can review this material with us. So thank you, and I hope you enjoy it.
Okay, good morning, good afternoon, good evening from wherever you are. My name is Eric Larson. I am the training specialist here at Altair, and I am here today to talk to you about OptiStruct. We're going to talk about, first we're going to talk about OptiStruct in a linear analysis capability, the capabilities of it for linear analysis, and then we'll take a quick look at the optimization capabilities of OptiStruct. Now, if you attended my session a couple of days ago, I'll mention it again here. This is definitely not meant as a comprehensive training. This is to show off the capabilities that we have and let you know what is available out there. And then there are many different routes you can pursue to get formally trained on the software. As Darius had mentioned, we do have our academia site, altairuniversity.com. Can also be reached directly from the altair.com website. There are numerous self-learning or self-paced learning programs on there. We do offer training sessions in our offices around the country, and please feel free to get in touch with us and see what we can do to help you out getting trained in the software. So with that being said, let's get going. Now, to talk about OptiStruct, or to show you what OptiStruct's capable of, we don't show you OptiStruct. OptiStruct is a solver. It's an interface that pops up when you tell it to run an analysis. So really, when we talk about OptiStruct, what we're talking about is the pre and the post-processing, the capabilities that the solver has, as well as how we go about setting up those analyses in HyperMesh, and then taking a look at the results in HyperView. So I've got some models here that I want to talk about. The first thing I'm going to talk about, and we'll kind of go from the most simple to more complex, and we'll just start with a standard linear static analysis. So if we're doing a standard linear static analysis, we're analyzing something in the elastic region of the material, and we're considering this as an analysis that when we apply a force to the model will spring back immediately upon release of that force. So it's a simple linear static analysis. And in HyperMesh, we can set that up. If you attended my session a couple days ago, you saw the capabilities for geometry cleanup and meshing. So I'm coming in here with a pre-meshed model. But for creating a linear static analysis, it's just a simple matter of indicating the loads that are going on the model, the constraints that are holding the model in place, and then telling the solver the specific instructions on how to run the analysis. So within HyperMesh, we organize our loads into what we call load collectors. So if I create that load collector, call it force or whatever, we've got one already called force in there, so I'll have to call it something else. Or we'll just leave it as load collector 1. But now any load that I create, so I can come up here to BCs for boundary conditions, create. I have forces, I have moments, I have pressures, I have temperatures, so anything that you could possibly want as an input into the system we can create. So I would just perhaps say a simple force, and I can select a node to put that force on, give it a direction, x-axis, y-axis, z-axis, or use these n1, n2, n3 options here to specify a vector that doesn't align with an axis. Give it a magnitude. I'll just create a dummy one here. And click Create. Let me reject that, and we'll do -1 so it comes out the other side. Click Create, and now you can see that that force has been applied. So this is the way that we set up our linear static analyses. We put forces, we put moments, we put pressures, even temperatures can be applied. Then, of course, we need to create our constraints. What is holding our model in place? Constraints are meant to represent the connections to a ground or some way of making sure that the model stays in location. We need a separate load collector for those, so I'd come in here and I'd create another load collector, and I'd perhaps call it constraint. And you can also come and change the color so you can differentiate between the loads and different load collectors. And then from BCs, it's just create a constraint. And a constraint is going to create a single point constraint, an SPC, a removal of any of the 6 degrees of freedom that any node has. By default, all 6 degrees of freedom are withheld. So I pick a node, I create that, and it creates that constraint. Now let me just put this in wireframe so you can see what it's done here. You see it's created this little triangle which represents a constraint and indicates the degrees of freedom which are removed from that node. If I choose another node, say this one up here, and I'll free up a couple of degrees of freedom. We'll allow it to translate and rotate about the y-axis. I click create, and you see now it indicates just 1, 3, 4, 6. So like I said, to talk about how we do or what OptiStruct is capable of, it's talking about how we set up analyses in HyperMesh. So you see now that we can create loads, we can create pressures, moments, temperatures, we can create constraints, and then it's now just a matter of creating a load step, which is a combination of a load and a constraint and an instruction to the solver to run a specific type of analysis. And so when I do that, I tell it what type of analysis I want. You can see we have a tremendous amount of choices here, and we'll cover some of these, but linear static is what I'm looking at right now, but we'll also cover normal modes, linear buckling, and inertia relief analysis. So linear static, and then I just tell it, okay, these are the constraints that I want to include in this analysis. These are the forces I want to include in this analysis. I can give it a name. We could come up here and say, okay, this is left turn. And now I click close, and I have this load step. And this load step now is an analysis that will be run in the solver. And because of the load step, what I can do is I can set up multiple cases. So say I wanted to do a right turn. I can come up here, create another load step, or right-click in my model browser and create a load step. And then I would say another linear static, and I could have my same constraints, but I could have another load collector, which would be the forces that this part would incur in a right turn, or braking, or whatever. So you can set up as many analyses as you want to run at the same time. And when you're all set, it's just a matter of now coming down here to Analysis, OptiStruct, telling it where you want to save the file. And in this case, I'm going to say Analysis because I want this to be an analysis only. I click OptiStruct, and the analysis runs. And I won't bore you with the analysis. I fortunately have the results right here. So now once that analysis has been run, we can bring the results into Hyperview, and a little bit fast there, we can contour the stress and see how our part is stressing. So you see that in this particular analysis we had a force going down. I think there was only one subcase in this, and it's deforming this part and stressing it accordingly. So OptiStruct can do standard linear static analyses. Now, some of the more advanced linear analyses, we'll talk about a modal. So many times when we're designing parts, we want to understand the natural frequencies of our part. We want to make sure that our part doesn't resonate at a specific natural frequency for vehicle noise harshness or worst case failure. Well, I'm sure we're all engineering students at one point or another. We've seen that video probably many, many, many times of the Tacoma Narrows Bridge. So we know what can happen when things happen at a resonant frequency. So we oftentimes want to know what our part, or what the resonant frequencies of our part are. So we set this up in just the same way that we did before, with the meshing, the geometry cleanup, the meshing, the addition of constraints, any loads that we want, and then we just add another load collector. So we create a load collector, and in this case, we're going to create it, and we're going to give it a card image of Eiger L. And that will be the instruction to pull the eigenvalues from the analysis. So we come here to the one that was already set up. With the Eiger L card, we have the option of specifying one or all three of these options here, V1, V2, and ND. V1 is the low frequency, V2 is the high frequency, and ND is the number of modes we want to pull. So say, for instance, I wanted to know all modes between 0 and 100 hertz. I would set it up like that, and that would be the instruction to the solver to say, give me everything you've got between 0 and 100 hertz. Or if I wanted to know everything between 50 and 100 hertz, now this would spit out everything between 50 and 100 hertz. Or I don't know what the frequencies are, so I'll leave those blank, and I'll put in 10 here in the ND, and now what it will do is the result will tell me the first 10 natural frequencies of my model. So it doesn't matter what the frequencies are. Or I could say between 0 and 1,000, 1,000, and indicate the 10, and now it would just give me the first 10 between 0 and 1,000. So you can see we can play around with those three request values to indicate the modes that we want, and it will run the analysis and spit those modes out. And again, I won't bore you with the analysis. We can look at those right here. So this is the modal animation. So we see that's our first mode. In this analysis, 6 modes were requested. I can go to our second mode, and now we'll see what the second mode is. Now, the degree of deformation. If you know anything about modal analyses, we don't pay any attention to how much this is deforming. It's just the shape that we're concerned about. So we can go through and see the different mode shapes. So modal analysis not only tells us what the frequencies are, and if we look at this list here, I know that my first frequency in this is 398 hertz, 3.98 times 10 to the 2. My next is 538.7, and then I move into the thousands, 1142. So I get an idea of what my frequencies are. And I know now that if, say, I wanted to make sure that my part had frequencies above 500, I've missed my target, and I'd have to make some sort of change to my part. Or, and we'll do a shameless lead into what I'm talking about later, we could allow OptiStruct to do that job for us. We could tell OptiStruct, I don't want to see any natural frequencies below 500 hertz, and allow it to design a part for us as a result of that. Okay, so linear, modal. An offshoot of the modal is the next type of analysis we're going to talk about, which is the buckling. So buckling analysis is now a failure analysis. We want to know what our part will buckle at. Now, buckling is perhaps a lesser known, or everyone knows what buckling is, but doesn't know what causes buckling. Buckling is actually not a failure of the material. Buckling is a failure of the design. We oftentimes will buckle before our part even reaches the yield stress of the material. So buckling is a very important analysis, and the way that buckling works is we do an analysis just like we did with the modal setup, and we request our Eiger-L information here. But when we set up our load step, you'll see we're going to set this up as a linear buckling. And with the linear buckling, it looks for a stat sub, which is the linear static analysis, with that and the constraints, and then applies the Eiger-L analysis to pull the eigenvalues out. And now the eigenvalues become what we call buckling load factors. They're not the modal frequencies anymore, but they're the buckling load factors. And if we look at the results of this part right here, you'll see I have all of these BLFs. And what the BLF is, the buckling load factor, so this eigenvalue right here, 3.02, it's a multiplication times factor that needs to be applied to the load on the model. So what I know here is if I apply 3.02 times the load that's on this model, the part will buckle, and it will buckle in this area here. And I can even put a little animation on this. So you'll see you'll get this buckle in. This is a wing, by the way. So the outer skin of the wing will buckle in this area here at 3.2 times the load. And again, you're seeing this happen not necessarily because the material has failed, but because the structure buckles at that. And then we can look at the different modes of buckling. So this one has shifted over to this other region. What you're not seeing is beneath this skin here, and let me remove that, are these ribs, and that's why it's buckling in these areas. So that was between those two ribs. This is between these two ribs. And now we've got a combination of both. So all of these are different buckling factors, and they're at multiplication factors of the load that's applied to the model. Now, the final type of analysis we're going to talk about is what we call an inertia relief analysis. Now, an inertia relief analysis was originally designed for aircraft in flight and for things in orbit. So if you think about the standard linear static analysis, we hold on to something. If you think about that control arm I had on, we were holding on to it at one end and applying a force at the other end. If you think of a cantilever beam, we ground it on one end and apply a force on the other end. Those are easy. We know how the part is being held, how it's attached. If you imagine an airplane in flight or a satellite in orbit, for instance, there are no constraints. There's nothing holding it in place. In theory, a sufficient force on it would send it off in any direction. But what holds that back, what prevents it from just flying off to infinity, is the inertia of the system. So the inertia relief analysis was created to utilize the inertia, or the inertial properties of any massive object, and use those as a constraining system. And we set that up in HyperMesh pretty much exactly the same way that we set up a normal analysis. But we do use a different type of constraint. We use a support 1 constraint. It's a special constraint that's created for an inertia relief. And then we set up a card, this parameter card. And if we come down here, we see we set this value in the parameter card in rel -1, which tells the solver that this is an inertia relief analysis. And then from there, it's just set up as a standard linear static analysis, but this specialized card here, the in-rel card, says don't just look for constraints and hold those in place. Look for these support constraints which create or which prevent rigid body motion, and do an inertia relief analysis. And, oops, wrong way. Let me go to that. So you'll see in this case, with my inertia relief analysis, when I animate this, even though there are no real constraints on this model, I am getting deformation from the, assuming from the firing of this thruster here. I'm getting localized deformation. And then I've got a number of different subcases that have been run here, and we can see all those. So inertia relief is kind of an advanced analysis used on airplanes in flight, satellites in orbit, and interestingly enough, used, and I used to do this a lot, used on control arms of vehicles. And I know, the standard one of these things is not like the others. What does a control arm have in common with an airplane in flight or a satellite in orbit? Well, the thing about the control arm is everywhere the control arm is loaded. So if we go, let me flip back to here because I got a control arm. If I want to analyze this control arm, I would be loading it here, here, and here, which happens to be the exact same places that it's being held onto. So a constraint would negate a force, and the inertia relief analysis actually allows you to do an analysis on a control arm. So oftentimes the inertia relief analysis pops up in weird places that you don't expect it to, and OptiStruct has that full capability to run those type of analyses. So we've got linear static, we have modal, buckling, and inertia relief analyses. So what I think I'll do now, because we're about 12:28, since this is the end of the linear analysis portion, I still have my optimization portion to go. Why don't we take a quick 5 minutes here, and if anyone has any questions, they can raise their hand or ask it, or I guess raise your hand or ask it in the question section. So if you have any specific questions about the linear static portion of OptiStruct, we'll spend 5 minutes, and then I'll go on to work on to tell you about the optimization.
Okay, thank you, Eric. Right now, we just have a...
I'm not hearing you. Did you hear?
Okay. Yeah. Currently, we do not have any.
Okay. Well, then we'll move directly on to the optimization portion. Okay. So OptiStruct is a world-class linear static solver. But OptiStruct is also an award-winning, industry-leading optimization code as well, thus the name OptiStruct. So what is optimization? Well, optimization is a way that we can utilize a software to help us understand what our part should look like, give us information about our part that is perhaps non-intuitive, and helps us fine-tune the design of our part. So what OptiStruct is all about is the ability to get information about our part in the early stages of design. So what I can do, let me come back to here. I'm going to talk about 3 different types of optimization that we can do. So let me open up a model here. Am I even broadcasting? Okay.
So when you say the screen, what does the screen show?
Okay, it just now says network connection has been reestablished. Okay. Okay, so it looked like we were having a little bit of a network issue here. I apologize if you guys missed anything. If somebody might tell me what was the last they heard, I can make sure that we cover the. Okay, yeah. If somebody in the chat window could just indicate where I cut out at, I can make sure that we cover everything. Beginning of inertia relief of the. Okay, excellent. Thank you, Diego. I appreciate that information. Okay, so excellent. So we got a couple of people mentioning where I left off at. So let me continue that that conversation, and then we'll move on to OptiStruct linear analysis. So what I was talking about in regards to inertia relief is a tool that we can use. It was, like I said, it was designed for aircraft in flight. It was designed for satellites in orbit and situations where the only thing keeping an entity or an object from moving or stopping moving is its inertia. But it also arises in interesting places, and conveniently the model I was going to use to talk about optimization is control arm. So I used to use inertia relief a lot in regards to control arms. So, and I understand control arms have very little in common with aircraft in flight or satellites in orbit. But when it comes to a control arm, and you guys are all Formula SAE, so I'm guessing you're probably pretty familiar with control arms. But the interesting thing about a control arm is, unlike a bracket on a car or a bracket anywhere that's welded in place and held in place, and then there's a force on it, a control arm is locked or is held on the vehicle at the 3 mounting points, and it's free to move. But the thing about the control arm are the places where it's held in place on the vehicle, the places that typically we would constrain it, are also the places that the loads are coming in. And so not only is it holding it in place at that location, it's also sending a load in at that location. And if I were to put a constraint on this, that constraint would negate any load that was being applied. So I can't load and constrain at the same location. So in inertia relief, even though I'm really not counting on the inertia of this part, it doesn't have a tremendous amount of it, especially in regards to the amount of force that's going into it. The inertia relief analysis, the way it works is it prevents a rigid body motion. So it will work in this case to prevent rigid body motion, kind of figure out what the net sum of the forces are, and allow the part to deform accordingly. So that's all I had talked about in regards to the control arm and the inertia relief. And since I was off, maybe you didn't hear me call for questions. So what I was going to do is, as we're halfway through, and next I'm moving on to linear static, I just wanted to ask if anybody had any questions about the linear static portion of OptiStruct. So we'll take a couple of minutes here if anyone has any questions, and then we'll move on to optimization.
Okay, the first question, Eric, is there a reference guide available for OptiStruct?
Yeah, so if you go into the, can you mute because I'm here.
Thank you, Eric. The next question is can you repeat how you activate inertia relief?
Absolutely. Oh, okay. Sorry. Can you hear me now? Okay. Okay. So the question was how to create or set up the inertia relief analysis. It's just simply a matter of establishing the parameter card here. So I can come to my analysis control cards, create my parameter card. And when I have my parameter card in here, oops, there we go. I just look down in my parameters for the INREL. I activate that and I give it a value of -1. Your options are 0, which says don't do inertia relief, which is the same as not having it selected. A -1, which is an inertia relief that relies on support constraints being applied. And then there's an INREL -2, which supposedly allows for you to do an inertia relief analysis and not use support constraints. It will figure it out on its own. I have no personal experience with that. All the inertia relief analyses I've done were with the INREL -1. So you can look into that as an option, and you won't have to create your support constraints, but I've always done the INREL -1. Okay. Okay, so I'll take more questions at the end here. I do want to move on to the optimization portion of today's program. So let me open up the optimization here. Okay, so when we talk about optimization, we're talking about a process of allowing the software to help us understand the needs of our part, or help us understand what our part should look like in a lot of cases. OptiStruct supports 6 different types of optimization: topology, topography, free size, free shape, size, shape, and that's it. Yeah, that's 6. We're going to talk about 3 of them today, the ones that are most widely used. And what the optimization code can do is help you understand your part, and help you understand your part at the beginning of the design process when you know the least amount about your part, but have the most freedom to affect changes on it. So the first type of optimization analysis that I'm going to talk about is the topology optimization. Topology optimization. In my many years of doing, understanding, and teaching topology, I think the best explanation of a topology optimization was actually inadvertently said by Michelangelo. So Michelangelo, 500 years ago, and I know you're thinking, why? The guy's talking to me about a 20th century, 21st century optimization technique, and he's quoting a 14th century sculptor. But Michelangelo said, that when he looks at a block of marble, he doesn't see a block of marble. I look at a block of marble, I see a block of marble. He, being the genius that he was, he looks at a block of marble. So imagine a block of marble sitting in front of you. He looks at it. He doesn't see that. What he sees is the statue inside of it. And it was utter genius. And of course, he said it in a far more elegant way than I'm capable of. But the idea was, if you take a chunk of material, so we'll imagine a block of marble, there is the perfect statue, the most beautiful statue you've ever seen inside of there. The material is already there. The earth did it for us. It gave us that statue. It just had the inconvenience of putting all of the rest of the material around it. So if we take a block of marble, to reveal that statue that Michelangelo sees, all he has to do, like it's easy, but what he has to do is remove the extra material around it. And that's what a sculptor does. And if you think about it, it's genius, of course, it's genius. He said it, but it's a genius statement. Inside any block of material, marble, wood, steel, aluminum, is a perfect statue, is a perfect part. And what separates it from that block of material is all of the rest of the stuff. And that, in a nutshell, is what topology analysis is. We take a block of material. Typically, we find the extents to which we can go. So take this control arm here. This would be an incredibly durable, incredibly heavy, and incredibly expensive control arm because it is a block of material. But this is ideal for a topology analysis. We give the topology code the material that we can give it. So we say, okay, there's something going on in this area here, so I can't go beyond that, and something going on in this area here, so I can't have any material above or beyond that. This is the upper limit and the lower limit, and I have to have it hogged out in here for something. So this is the maximum amount of material I have. This is my block of marble. Now, I want to find out what material of that is necessary. Now, we as engineers tend to over-design the heck of it out of things for a good reason. We don't want our car parts breaking, or even worse, we don't want our airplane parts breaking while the plane is in flight. So we over-design things. Well, the optimization code doesn't have that limitation. It knows how the force is progressing through the model. It knows where to put material, and that is what topology optimization does. And let me show you, of course, the results for this. So this is my initial part right here. What you'll see now is how the topology optimization works. It takes that initial chunk of material, whittles it away, and allows you, or basically tells you where material is necessary to achieve whatever goal you want. And this is the final design. So it is essentially designing a part for you by putting material where it's necessary. Now, how's it doing that? Well, let me pop back over here to HyperMesh. We set up the analysis just like we would with a normal linear static. We put forces on there. We put constraints on there. But we set up an optimization. We tell it, this is our design variable, and our design variable becomes all of these elements here, these red elements. And then we say, I want to measure some responses off of this, things I want to know. I want to know what the volume of it is at every iteration, and I want to know the displacement of some node at every iteration. Then we take and we constrain some of those. So if I come here and I review my constraints, what I've done is I have constrained this nodal displacement. So I believe it's this node right here. I've said that in this load step, I don't want that displacement to be more than 0.02. So I establish some limits on this. I believe also there's a stress constraint on here. So if you come here, nope, I guess they didn't include that on this. But you can include stress constraints. So you can say, these are the limits I want to go. And as we mentioned earlier in the modal analysis, I can say, I don't want my frequency to be above or below a certain value. And then I set an objective. And in this case, my objective is to minimize the volume of the part. So my goal is to use as little material as possible, but make sure that this node does not move beyond what I set my limits at. I don't see stress beyond what I set my limits at, and I get an optimization that looks like this. So it tells me what material is necessary. The next type of optimization is what we call a shape optimization. A shape optimization uses morphing in HyperMesh. So if I come back to my page 1 here, and I'll bring up my model, we have morphing in HyperMesh, which allows us to alter the shape of our part. And let me just show you how this was morphed. Apply shapes. Oops, I don't want to do all of them at once. I just want to do, I think it's shape 1 or shape 2. Yeah, there we go. Select and apply. So this part was morphed. You see the original curved circular part was morphed into a square. And the optimization now tells us what the optimum shape of that part should be, what the optimum shape of that tube should be to put a constraint on. So we're doing a response on the mass of the part and the stress of the part. The constraint in this case is saying that the stress cannot exceed 200 megapascals, and then our objective is to minimize the mass. Optimization is all about telling the solver what can be changed, what information you want to know, what limits we have on that information those responses we're pulling out, and what our goal is to minimize something. Minimize mass, minimize volume, minimize or maximize frequency, minimize compliance. Compliance is the inverse of stiffness. If I minimize the compliance, I make the part as stiff as possible. Optimization is incredibly easy within HyperMesh and OptiStruct. We set up our design variable, our responses, our constraints, and our objective, and it tells us what our part should look like. The last optimization is what we call a free size optimization. Free size optimization is great for your composites, and what free size optimization does is it again tells us what our part should look like by altering the thickness of elements. And if I do this with composites, it will tell me what the thickness of each composite is, or each composite layer and angle is. Sure. Let me come back to here. So morphing, the question was repeat what morphing is used for. So morphing in HyperMesh, if you leave optimization out of it, is say for instance I have a part and I want to change the shape of that part. So I have this part right here. It's all set up for an analysis. Now I'm told, hey, this tube needs to be square, not circular. Well, the traditional way of going about doing that is to bring in the new geometry, completely remesh it, completely reset up all of these RBEs here, these rigid elements, reset up the force, the properties, the materials, the constraints, and it would take a substantial amount of time. But with morphing, what I can do is apply a morph to these nodes and change the shape of the part without completely rebuilding it. So with morphing, what I can do is say, okay, I want this to be square or rectangular. And it alters the nodes, but it doesn't remesh the part. You'll notice that the force is still there, my rigids are still there, materials are still there. This part, I could run it instantly and now know what the stresses were with a square tube as opposed to a round tube. And when we talk about that in regards to optimization, as I mentioned, the design variable is simply stating what can we change in the part. Well, what we can change is the shape of this tube. Somewhere between a perfectly circular and a perfectly rectangular tube is an optimum shape that meets the requirements that we have, the limitations on stress, and minimizes the mass of the part. And it has determined that this oval shape, let me pause this and just take it to the final, that this oval shape, not quite round, not quite rectangular, is the optimum design for the part, and the morphing allowed us to do that. It provided that which we could change, which is the location of each of the nodes. So in this case, the element quality didn't deteriorate. We still have very good quality elements, and morphing does a very good job of moving the elements or moving the nodes without distorting the elements. But we do have, and this is definitely some more advanced morphing stuff, so I'll show you what we have the capability of doing. But just be aware that, where is it at? Somewhere in here. Assign, there, edit, nope, assign, domain parameters. That's what I was looking for. So we have the ability to set up parameters in here which will force it to remesh in the case that, or in the situation where our part gets too, or where our elements get too messed up. We can change the parameters and say, okay, in that case, go ahead and remesh it. So. So when I'm in HyperView and I have my final morph shape here, what I do is I export this as a solver deck, and what it will do is it will take the elements in the nodes and export them as either an Abacus, Dyna, OptiStruct, Nastran, Radios, or in an STL format. It will save this shape in a grid form, or as elements and nodes, and that can be then brought back into HyperMesh. And we can use a tool in HyperMesh called OS Smooth, or we can just directly create surfaces from the finite element model, or from the finite elements themselves. So we can ultimately bring that back into a CAD system. So there's obviously a tremendous amount more in regards to both the linear analysis and the optimization. This is just scratching the surface. Again, I'll direct you to altairuniversity.com, where you can get some personalized training stuff. There's some manuals on there. Again, there's the student version. Get a hold of that. It's free. It's great, and I'd encourage you to go there. Also, on the altairuniversity.com, we have a discussion forum moderated by Altair employees, but open to anyone to discuss. So ask questions there, pose ideas, and you'll get some great discussions and information out of that. Beyond that, I'll take questions for the next 5 minutes or so, but I'm done with everything I wanted to talk about. Yeah, absolutely. Yep. Yeah. Yeah. Altair University. So if you go to altairuniversity.com and view the academic program here, we do have these books. In there we have the multi-body simulation, structural optimization, something that I totally can't read, and then practical aspects of finite element simulation. You can request these books, you select them, and you put in your information here, and you will get a copy sent to you. As Darius mentioned, many universities are actually using this practical aspects of finite element simulation in coursework, but it's a great e-book or e-manual to help you out understanding more about finite element analysis, and that in combination with the other books we have here, Structural Optimization, MBD, and if you can read Japanese, I think that's Japanese, whatever this book is here. Is it Chinese? I don't know. So I apologize if I offended anyone out there. Some language, if you can read that, grab that book too.
Great, Eric. There are 2 more questions that were posted, and the first question is, do you need to know the exact mass distribution of your component to carry inertia relief analysis?
No, you don't. So when you set up the analysis, when I model a part, I'm creating an FE representation of some sort of geometry. Then I apply properties to my elements. If they're shell elements, that will give them thickness. And then I apply a material in there. So my material, if I come back here to HyperMesh, if I come here to my material, you'll see my material has this rho value here, which is the mass density of the part. So what HyperMesh and OptiStruct, or what OptiStruct will do, is based upon the elements and the thickness established in the property card and the density established in the material card, it will calculate the inertial properties for all of these parts and use those accordingly. You do have the ability to add non-structural mass to adjust that, but by default it will calculate all the inertial properties for you as long as you set up and model your model correctly with the correct shape and the correct material. It should be a pretty accurate material distributor, should be a pretty accurate inertial property on your model.
Excellent, Eric. Thank you. The next question was asked earlier, are there generic rules for placing and setting support 1? For example, how many degrees of freedoms to use?
Absolutely. So in the case of support 1, so when you do an inertial relief analysis, you can only use 6 total degrees of freedom. And just do a quick demonstration here. So the way that I've always done this is I've come to my constraints panel here, and this is probably the most important thing. Come down here to the load types, and you have to tell it support 1, otherwise you'll be creating SPCs. You'll immediately know it when you run your analysis because you'll see 3 red hot spots right around where you create those constraints. But I first switch it to support 1, and what I do is, so I have 6 total 6 total available degrees of freedom. So I come here to some sort of extremity of the part. So I'll come to here, and I'll create a 1, 2, 3. So I've used up 3 of my degrees of freedom. Then I'll come to another extremity of the part, right here, and whichever direction I moved in this case the z-axis, I'll remove that degree of freedom and create. So now I've used 1, 2, 3, 4, 5, come to the last direction here. In this case I moved in the x, so I'll yank that off of there, create. Now I've created a total of 6 degrees of freedom, and this orientation will prevent rigid body motion or rotation, which is what the support elements are designed to do. In general, where specifically you put them doesn't really affect the analysis. It may make the deformation look a little bit different because it kind of changes your frame of reference for the deformation, but your results will be the same, irrelevant of where you put them. Just find 3 points at extremities of your part, put 1 at 1, 2, 3, move in a direction, remove that direction, move in the third direction, remove that direction, and it will always give you 6 degrees of freedom properly oriented.
Thank you, Eric. Next question is someone who actually is using Inspire. So they're wondering, is it possible to transfer an analysis or optimization done in Inspire into HyperWorks environment? How would you do this?
Okay, so we're going to show you a little behind the scenes action of Inspire. So I'm going to come here, I'm going to say File, New, Model. I'm going to blank this out completely. Now, what you may or perhaps may not know is when you run Inspire, Inspire is invoking OptiStruct. Inspire, for those of you who don't know, and I think there is an Inspire session, right? Okay, so make sure you hop in the Inspire session. Inspire rocks.
Yes, and it's the last session for next Thursday about the concept tool for optimization. That's the session about Inspire. It's maybe not as obvious as it needs to be, but it's a really user-friendly tool to do structural analysis and optimization.
Yeah, so Inspire, that very first one I showed you, the topology optimization, that's all Inspire. Inspire is great. It does that incredibly easily and incredibly well, and it utilizes OptiStruct, which means that if I come here to import a solver deck and I'm going to sneak into a little hidden area on my computer, it's actually not hidden, but you may not know it's there. In my documents directory, under solid thinking, 2014 is the latest version of Inspire. Under Inspire, under optimization, it writes out all of these directories. And in these directories is an FEM file. And that's the FEM file that Inspire has generated to go to OptiStruct. And if I import that in, and for whatever reason, it always makes my constraints and my loads incredibly large. And then we'll just come to my forces here, uniform size 1. That's better. And now you'll see this part was actually set up in Inspire, but I can read it into HyperMesh, and it's a great learning tool. You can set it up easily in Inspire and then see what it did to create the OptiStruct model, and you could take this OptiStruct model and you could make some changes in HyperMesh and rerun it again. So there is a bit of interconnectivity between the two. You just have to kind of know the secret hiding place as to where it's dumping the files.
Again, if you can repeat that location.
Yeah, so by default, it's in your My Documents directory. So in your My Documents directory, in a solid thinking, 2014 or whatever version you're using, Inspire, optimization. Now, if you forget that, and if you bear with me just a second here, let me pop up Inspire. Hopefully it'll come up real quickly here. I'll show you where to find that path, or perhaps where to even change that path if you want to. So I'm taking away from Raul's presentation.
Well, I also want to let you know part of the free student edition, Inspired, comes along with that too. So the nice thing about the student edition, you get our complete HyperWorks package up to almost the most recent software that we've added to it. The only thing that's not in there is the new electromagnetic solver that we have, FACO. But otherwise, you have everything else that we also offer.
Yeah, and just to mention, so with the student edition of Hyper Mesh, there is a limitation of 10,000 nodes. The Inspire is provided fully functional, and there are no limitations on it whatsoever. So we're all about giving Inspire to EDU folks, and you can even get Inspire separately on its own. But if you come into Inspire, and this is Inspire, it's a great program. If you do not take nothing else out of this, and hopefully you took more than this, come back next Thursday and see Inspire. It's awesome. But if you come here to Preferences, and then you go to, I believe it's under Optimization, you see this Run History path. See users, Eric, documents, solid thinking 2014. This should look relatively familiar considering we just went to this. So this is where that path is, and you can change this value. So you can bring in the stuff that Inspire creates into HyperMesh and play with it in there.
Excellent, thank you. Hopefully we have time to get the 2 more questions that were asked.
Yep.
Are all the optimization tools based on the IMP algorithm? Is it possible to have control of the penalization factors?
We don't use a penalty method. I believe for our optimization is based on a density method, and you're really trying or not trying, but you're really pushing the limits of my knowledge of how the optimization works. But our optimization works on a density factor, not a penalty factor. The density, what it does in a topology optimization is it varies the density of the part. And when I say density, I'm not talking about the material density. It's like a density of usefulness. Essentially, it's a value between 0 and 1 that it multiplies to the Young's modulus of every element. So if you think about the Young's modulus, it's everything the element can give. It's the full strength of the element. If you multiply that by a factor less than 1, then that element is not contributing everything it can get. And if you multiply it by 0, and actually it's not 0 because 0 would throw mathematics all into a tizzy, so it's a number incredibly close to 0, then that element is contributing nothing. And that's how it determines which elements are used and unused. So it's a density, not a penalty method. And unfortunately, if you need more information than that, I can't give you any more. Pardon me? Yeah, through the Theory Manual Online. Darius just recommended that. That's the extent of my knowledge of what goes on in the background, but you can look in the Theory Manual, and that might help you as well. So we got one more question?
Well, in addition to that question, what I wanted to let everybody be aware of, again, there's so much to be aware of for OptiStruct and doing FEA analysis and optimization. I just put a link in the chat window, and you might want to click on that link to save it, bookmark it. But we have self-paced training material available free. You just need to go there, and you can go through different exercises there, especially once you have the student version. And then proceed along to learn more about OptiStruct. So that's another great asset there for you to use and available. You could use it at any time you need. We know students like to do a lot of their work at midnight, so that's why that's good. All right. So now for the last. Well, we have more questions, but let me just take a quick look to see if we can get to them, and so this will be the last question here. Eric. So the question is regarding the optimization objective. Is it possible to weigh mass reduction difference than the stiffness parameter and moment of inertia? How specific or flexible is the target? So to me, it sounds like you're trying to get a weighting or of multiple fields.
Yeah, so we can do weighted compliance. As for a weighted mass, I'm not so sure about that. So when we set an optimization, so we can do a, let me come here to optimization responses. So I can set a response for weighted compliance, and I can do weighted frequency, but I don't see anything for like a weighted mass. So weighted compliance actually is used primarily when you're looking to incorporate multiple load steps. So if I have many different load steps in my model and I want to optimize shape that kind of takes into account all of them, the weighted compliance allows me to select those and weight them accordingly, and then I can optimize against that. So we do have weighted compliance, weighted frequency. I don't know if we necessarily can put weights onto mass reduction. But again, that's a question that you could ask in the forum, or take a look in the manuals we have and see if there's an answer in there.
We're going to thank you, Eric. What I would like to do now is we go to our polling questions, so we can proceed there. You want to launch those, please, Eric? Great. So the first question is, would you like a member of our team to follow up with you for further trainings? So we know there's a lot of material here. There's also some material that we can point you to, like the self-paced material. But if we can, if you have a site that's close to us, we can probably try to arrange a meeting or with you and the rest of your team or your department to talk more about how OptiStruct or one of our other tools can help you out more. So we'll just wait a little bit longer here to get a chance for a few more people to vote. So even if you are not interested, please just say no, and we will know that you have no interest in that, and go from there. So I have about 5 more seconds, and we'll close the poll. Great, thank you for answering that question. The next one is, we would like to make sure that we can provide these type of trainings at a better time. We know this is really at the end of the cycle for most of the competition teams in Formula SAE, and right now you're doing the final tune-ups for the upcoming competitions. But we know that analysis would be much better if you can get this done earlier in the cycle. So we put a few choices on here. Please pick a choice that if that you think will work out best for your team to see this or other material that we present. In the future, we're looking at presenting a topic called, the practical aspects of virtual wind tunnel, which is, again, a very similar interface to Inspire that allows you to put your geometry in there and the type of constraints or loading conditions for CFD analysis, and then it runs our solver AccuSolve in the background, and it will display the results of that. So again, another very powerful tool like Inspired. All right, so we got most people that answer. We'll just give you a couple more seconds here to see if anybody else. But all right, we are done. Thank you again. So we do like to thank you for attending. Everybody that has attended and anybody that has registered will receive a link to this later today. And if you do experience any difficulties with that, or please just contact us and we will get back to you. But again, we really appreciate your time and hope this was of benefit to you all, and have a great weekend. Take care, everybody. Bye-bye.
Bye. Thanks, everyone.